Number 17 is asking which of the following compounds is diamagnetic and won't interact with a magnetic field. Okay, so we want to pick the one that will have no unpaired electrons. So to do this, we need to be able to go through, pick out the transition metal, and identify its charge so that we can get its electron configuration correct. And so you can see that for A, I've identified cobalt as 2+. And the reason for this is because we know Cn has a negative charge, and there are 6 of them. So that will have a -6 overall contribution. And the whole thing is -4. So for this to work out, the cobalt would have to be +2. Okay, so that's how I identified cobalt as being +2. And so if we go to write the electron configuration of cobalt, 2+, we start with argon. And how I usually do it is I write out the full electron configuration and then remove any electrons for the positive charge. So I'm going to go ahead and start, knowing that I have 9 electrons that I need to draw in from here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's just cobalt. Then I'm going to erase 2 for the 2+. I'm going to erase those from the 4s. Okay. Even though the 4s is technically lower energy, it's further away from the nucleus, and it's easier to pick the electrons off out of that orbital. Okay. So now that I have the configuration for that, we have to take it and put the electrons in this crystal field theory diagram, because we know that not all d orbitals are created equally. And in the problem, they tell us that this is low spin. So low spin means we're going to keep as many electrons as we can down in the bottom. Okay, so I have 7 d electrons that I need to draw. So I'll have 1, 2, 3, low spins I'm going to keep in the bottom, 4, 5, 6. Now that I've run out of room in the bottom, I'll put one in the top for 7. Okay. And so here we do have an unpaired electron. And so this would be paramagnetic. Okay. And it would interact with the magnetic field. So A is not an option. Okay, so now let's look at B. We have COF6 3-. So we know that fluorine is going to exist in water as fluoride, which has a negative charge. There's 6 for a contribution of overall -6. The complex has a charge of -3. So that means the cobalt here must have a charge of +3. That's how I arrived at cobalt 3+. So let's adjust the electron configuration that we already have for cobalt 2+ and make it for 3+. I'm just going to get rid of one of my paired electrons. And then we'll start with a new crystal field splitting diagram. Okay, so I erased the diagram below because now we're not in a position of having low spin. Now they tell us that we have a high spin. So some of those electrons will be able to go up to the top. So now I have 6 electrons to draw. So I'll go 1, 2, 3, 4, 5, 6. Okay. And hopefully it's clear that we have unpaired electrons here. So B is definitely not going to be an option. And C, this option's a typo because it would give us neutral iron, which just doesn't make sense in water. So we're eliminating C. And then we can go on to think about D. We have iron hydroxide here, or hexahydroxide. And we know that OH will exist in water as OH minus. So again, we have our -6 case. And this is overall -3. So the iron must be +3. Okay. And in the electron configuration for iron, we have 8 total electrons to count for after argon. So I'll start 1, 2, 3, 4, 5, 6, 7, 8. So this is just straight iron. Well, we want iron 3+. So we're going to have to get rid of some electrons. So we'll get rid of the 2 in the 4s first. And then we'll get rid of the paired electron, the D. Okay, so now we have the electrons we have to work with, those 5 D electrons. And they tell us high spin. So we can draw our electrons in again. 1, 2, 3. It's high, so we can go up. 4, 5. Again, we have unpaired electrons, so that is not an option. So in E, we have copper hexabromide. And we know bromide will exist as -1, giving us a total of -6 again. This is equal to an overall of -4, so the copper must be +2. And so we can go ahead and start by writing the electron configuration for just copper metal. And copper is one of the funny ones, where we have something that's half filled. And so we have the 4s electron jump up to make that happen. Okay, so this is the electron configuration for copper, even though it seems strange. And chromium's the other strange one, where instead of having everything paired here, we have everything half paired. Okay, but you still have the 4s electron jump up. Okay, and we actually care about copper 2+. So go ahead and get rid of our s electron first, and then one of our paired electrons. Okay. And then we can go ahead and fill in our electrons. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and so we see here that we still have an unpaired electron. So this one also would be magnetic. So you might be sitting there being like, we didn't get an answer. And you'd be right. So let's just adjust for the typo. Let's go ahead and assume that they actually wanted number C to be Fe CO6 2+. So CO is neutral. So the 4 diagrams we drew all corresponded to magnetic compounds, which would give us no correct answer. So let's adjust the problem to kind of account for the typo on this problem with number C, or letter C. let's say that the complex instead were FeCO 2+. And let's just do it again. So we'd have CO, which is neutral, making our iron Fe2+. Okay, so let's try it that way. So we can write the electron configuration for Fe first. We'll start with 8 electrons, but we actually want the 2+ configuration, so we can go ahead and get rid of those pesky 4s electrons. Okay, so now we have 6 electrons, and then over here on the left it says low spin. So let's go ahead and fill out the diagram. 1, 2, 3, 4, 5, 6. Okay, so now hopefully you can see these are all paired. And so this iron 2+ low spin would be diamagnetic, which is not magnetic. So I like to think of it as if the magnetism dies. Okay, so that problem had a typo problem with it, but the logic is still good. Number 18 is talking to us about photosynthesis. So it's how plants store energy. And, let's do this problem in green because it's about plants. Yeah. So energy here is a reagent, which would make this kind of endergonic, as we would say. So let's go through and evaluate each of these 4 true or false statements. So the first says the activation energy for the reverse reaction is lower than the forward reaction. So I think we can think about this in terms of those reaction coordinate diagrams that we used to work with a lot. So we can think of reaction progress as being on the x-axis and energy on the y. And we start with our reactants, which are going to be the CO2 and water. And we know we have to put in energy to make our products. So the products are going to be at a higher energy state. And then we'll have our activation barrier. Okay. So looking at this diagram, going forward, we have this big mountain to go over. And going in the reverse direction, there's still a hump, but it's not as big. Okay, so I would say that the first answer is true. Okay. And then the second option says catalysts increase the production of C6H12O6 by increasing KEQ. There's one thing you guys remember. Well, there's a lot of things I want you guys to remember. But I want you to remember that catalysts don't change where the equilibrium sits. It just changes how quickly we get there. Okay, so all catalysts would do is kind of change the activation barrier. A little more dramatic than that. Making it easier to get over the hump. But the ratios stay the same. And without a catalyst, the reaction could still go. We could mix some CO2 and some water together. And eventually, might be thousands of years from now, we would start making some sugar and oxygen. Okay, so the reaction can proceed without a catalyst. just has such a big hump to get over. That makes it really slow. So 3 is false. And 4 I've kind of already alluded to. But it says a catalyst won't change the free energy of the products. And that is true, because we'll still end at the same final energy, regardless of whether there's a catalyst or not. We just change the pathway to get to that final state. Okay, so 1 and 4 are true here, which makes C the answer. Okay, number 19, we have a coordination compound. They want us to figure out the charge on the complex, on the metal, and the coordination metal, number of the metal. Okay, so we have this complex and it's K2. So that means it has 2 potassiums with it, if we were to have this complex as a salt. We know that potassium is a +1 charge, so this complex must be -2. Okay, so that already kind of really narrows down our answers. Let's keep going. So we have 2 types of ligands here. We have CN. We know CN has this -1 charge. We'll use that in a second. But also, it can only coordinate with a metal in one way. So this is going to be monodentate. Okay. The EN molecule, hopefully you guys recognize it from all of the homework problems you've been doing, but this is bidentate. Okay, it can wrap around and coordinate the metal in 2 spaces. So we have, for the coordination number, we'll have 2 from the EN, and then 4 from our 4 cyanides. So we'll have a coordination number of 6. So we can already see that the answer is D, but let's go ahead and check the oxidation state of the metal. So the cyanide has a -1 charge, and the EN is neutral. So we have 4 cyanides for a total of -4. Overall, we're -2. So the oxidation state on the metal must be +2, which aligns with option D. Oh, the Haber process. We're going to use this for the next 2 problems. If you guys know me well, then you know that I'm not a fan of the Haber process. Just because we use it in a lot of examples. It's cool, fertilizer. Okay, but anyway. We have some scientists trying to catalyze the Haber process, and we have some mechanism. They want us to get the rate law. When you have a rate mechanism like this, we're going to write it always in terms of the slow step. And so here, the slow step is the first step. And so we can go ahead and write our rate law in terms of this. We have rate is going to be equal to some K times N2, concentration, just to the power of 1 because there's no coefficient, times Fe magic ligand 6 concentration. Okay. And so because the first step was the slow step, this problem's actually really straightforward because we can leave our rate law in terms of things we're adding. And we're adding nitrogen when we're adding our catalyst. So we can just leave it like this. We don't have to do any replacements. Okay. So that's just E. And then if we go on to number 21, you can see that, oh, there's a competing group of scientists who have a different mechanism. And they give us this table of data. And we're trying to figure out what the rate law would be. So when we have data like these, we want to pick two experiments to compare where the nitrogen concentration changes, hydrogen stays the same. So if we look from experiment 1 to experiment 2, we can see that we've doubled the amount of nitrogen. Hydrogen stays the same. And then we can look at how the rate changes. And so when we doubled the nitrogen, we see a quadrupling in the rate. And when that happens, that tells us that nitrogen is second order. Any change will see the square of its effect. So we know our rate. We're going to have some K and 2 squared. Okay, and then we can use the same kind of logic for hydrogen. So we want to find the two experiments to compare where the nitrogen stays the same but the hydrogen changes. We're going to compare experiments 1 and 3 where we double our hydrogen concentration, and then we look and we see that our rate doubled. 3 times to our hydrogen concentration times 2 rate. And so this is going to be first order. Okay, so that will be our rate expression, and that matches also to E.